Yo, what's up, guys? Today we'll talk about the KMP algorithm. It is an algorithm used to find the occurrence of a given pattern in the text, just as shown as the above. And then it's created by these three computer scientists: James H. Morris, Van Pratt, and Donald Knuth. And so at first we'll talk about the standard way, which is like this. We look at each character, the X and the X. We see that it's the same. Okay, we continue. It's still the same. Continue. We see. Wait, no, sorry. This is not what I meant to say. So this is the same. This is also same, and this is different. So then we will just go here and compare it. It's the same. It's different. Come here. It's different. Continue. It's different. It's same. It's same. It's same. It's different. It's same. It's same. It's different. Since when there's a different, we will just go back. Go front by one, and then that's how we just get here, which then will be correct. However, for the KMP algorithm, the main point is to use the information we already know to avoid doing stuff like that. Because obviously, the worst case scenario will have a time usage of n times m, and n is the length of the pattern, while m is the length of the text. So the KMP algorithm will make the time consumption be n plus m, which means it'll only iterate through this once and this also once. So proof it. So now, but at first we need to learn how to create this thing called a next array. So at first we have the xxx, and then for the next, like the value for the first letter in the next array, it will always be 0. And then here, and then we go to the second one. So now we have 2x. So the prefix will be x, which is the first letter, since the prefix cannot be itself. That is also why the first letter will always be 0. And the suffix will also be x, which is all the letters from the behind, excluding itself. So, and x have a length of 1 because it's obviously one character. And then now we're to xxx. They have a prefix of x and xx, and a suffix of x, which is here, and xx. So now we see that the biggest the biggest common prefix suffix is xx, which have a length of 2. And now we go to xxxx. We have a length of xx. We have x, xx, xxx. We exclude itself, so we have these. And then for the suffix, we have x, xx, and xxx. So now we see that the length of it is 3. Now we will do another example with, let's say, A, B, C, A, B. Alright. A, B, B. Yeah, well, I will just use this. So first, the first letter will always be 0. And then, now we're at the AB. So it will be A, and which is this, since it cannot be the whole thing. And then the suffix will be B. And then we see that there's no common prefix suffix, so it'll be a 0. And then we're to our ABA, and we see there's an A, and then there's an AB, and then we see there's an A right here, and then we see there's a BA. So that's 1, since AB and BA is not the same thing, so yeah. And then now we're at ABAB. So there's AB, AB, sorry, and then ABA. Sorry. And then now we're at our suffix. It's B, AB, and BAB. We realized that the only like ones that are the same is AB, and it have a length of 2 since there's only 2 characters. So the next array for this one will be 0, 0, and 1 and 2, obviously. And so this is why we only need to iterate through the pattern once and only once. And now we're to our text. And so now let's see. We'll compare this just like normally. X and X is the same. So we'll I'll actually give it like this I index for like the text and a J index for the pattern. And then when they're same, both I and J adds 1. So now it's here. It's the same, so it adds 1 again. And now it's here. But we see that, ooh, this is wrong. Because Y and X, that's not the same. So now what will happen is we'll look at J. If J is 0, which is the first letter of the pattern, if it's not the first letter of the pattern, which is the case right now, then we'll look at the index, like the value before this J. So J is currently here, so we will look at the value of this one, which is 1. And 1, it's here. So that means we can compare these. Wait, sorry. Not this one, but like this one. And then these, we see that it's different. However, our J, so now we compare the X and Z because this is 1, so it will be X, and after we just add both ones, it will be like here. Wait, no. Wait, let me think about it. Oh, sorry. Let me restart. So after the X equal to X, we both of the I and the J plus 1, so it's here. The X and the X is still same, so plus 1. And the Y and the X, they're different. So we look at the value for the array, which is like before this letter, which is 1. So we go to index 1 of the pattern, which is X. And then we move it here. We see like when it's different and the J is not equal to 0, then it will just like the J will be the one in front of the original letter, which is this X. So now it'll be it will be equal to the, I don't know, it's hard to explain this, to this 1 right here for the, so it'll be like the second letter since we're talking about computer science right now. So it'll be this 1 right here, which is equal to this X. And then we compare it, we see, oh, damn, it's still different. And since J is not 0 right now, we'll go in front, which is this X. And this X, it's 0. So now, and for this one, now we'll go to the number in the next array that's behind this thing, which is 0. And then 0 it refers to the one here because this is a 0th letter. So now we go here. We see that it's still different, but our J is at 0 already, so we need to move the I. So I'll actually move the I now, and then I will come here, and that means we will also move the J. And then we see, oh shoot, it's still different, but the J is already at 0. We cannot move no more, so we need to move I. So we put I here, and then here, and then now we see the same. So we make I go in front one block, J also go in front one block. Still the same. I go here, J go here, and then we make the J go here to compare, and we see that they're different. So then J will go to the one before the current J, which is 2. And then, so like if currently the value for this next array is 0, then the J will move here. But currently the J is like 2, so it will be here. So it will just move to the position of the next array. So I could do, and then now we'll just compare these two, which is obviously not the same. So now the J will be go in front, go back one block, and it's 1, so it's this X. And then we compare again. We see it's still the wrong, so we will just move this one here. And then now we see the J is 0. We cannot move it no more, so we will move I. And then we will, like, this is basically the idea. So there's like the most simple way to do this, like to find the next array, is we have a for loop, and then this is basically the code, and then the substring will be equal, like every time it'll be equal to 1 more of the pattern. So at first it'll be A, and then it'll be AC, and then it'll be ACA. And then what we'll do is we'll find all the prefix of it and all the suffix of it. And then, so we will start with the biggest prefix and suffix we can find. And if they're not the same, we'll make it like smaller. So this is basically the point of the code. It's like this. And then if we cannot find any, the value for the next array at that position will be 0. Otherwise, it will be the length of the longest prefix suffix. And then this is like, but this is actually not the best way to do it, because this is not really a time complexity of n. So I will show you guys what the time complexity of n is. It's using doing it like this one. But I will not really explain deep in this, because this is just a really basic tutorial about KMP algorithm. So if we get into this, how to calculate this next array, that would be really complex. And I don't really get like the whole thing. And then so now this is basically how we calculate the next array. And then how we calculate, like, we just iterate through everything. If the text and the pattern are the same, then we will detect if like this J pointer, if it's at the end of the pattern, and if it is, we will like pause and then just print out like the index of the I pointer minus the length of the pattern. Otherwise, if m is 0 and text is like doesn't equal to m, like if the pattern and the text is not the same and m is 0, we'll just continue because I is always like increasing. However, if m is not equal to 0 and text is non-m, like if this index is not 0 and the text and the pattern is not the same, we'll make I minus, we'll make the I minus minus and m will equal to ARRM minus 1, which is basically, it will equal to like the 3 minus 1 in the array, which is 2, obviously. And then it will point to whichever this position leads to. I will minus minus because like we cannot let I increase, but like since it's always increasing, we'll just like let it minus. So let's say we are having this thing, and then we are having xxx. We'll print out stc out. I'll just show you guys like the code. Basically, you see this is it'll print out every prefix and suffix, and then no, never mind. It will print out every substring of the string, and then it will identify the prefix and suffix and find which one's the longest. And this is an index of where xxxx is first found, which is correct. I think. I'm pretty sure. But if we put one here, now it'll be different. It will say 4, which is correct. 0, 1, 2, 3, 4. And that's basically the code and the fundamental of KMP algorithm. Thanks for watching. Bye.